All right, so we're gonna continue this. We're gonna finish up gases today. And then on Friday and next week, we're gonna talk about intermolecular forces and phase change in more depth. So some of that should seem kind of familiar because we've talked about those phase diagrams a little bit already with the three phases. We're actually gonna go over that in more detail. But just to start off, the one last random question that I had from last quiz asked about what the heck is thermodynamics and how does that affect things? I'm not sure if that was a question that because I said the word thermodynamics or just because somebody Googled the question, what's a question about chemistry? But it is a good question. So the whole point of thermodynamics is basically applying statistics to molecules. And so I've already drawn this equation up here before, and but basically what winds up happening is that all molecules, and this is going to wind up being important in a few minutes when we talk about gases and how gases move. Basically, molecules don't all have the same energy at any given point. When you measure the temperature of something, you're measuring indirectly the average kinetic energy of the molecules. So higher temperature, the molecules are moving faster on average, but that's still an average. But the thing is, it doesn't behave like a real bell curve. It kind of seems like they should be normally distributed, right? Those of you who have had stats, most things numerically, if they're truly random, most things are a bell curve, right? Thing is, you can't really have a bell curve because if you looked at like the energy of molecules, if we said, okay, our average kinetic energy of our molecules is some number. Well, if it was a bell curve, it would be equally distributed both directions, right? We'd have something that looked like this. Seems like that would make sense, that our number of molecules would be, most of our molecules would be centered right around the average, but then it'd fall off like a bell curve. Except if this is kinetic energy of molecules, what's wrong with this graph the way it's drawn? If this is 0, can you have negative kinetic energy? Not if we're just talking about molecules moving around, right? So thermodynamics really got started because a physicist and mathematician named Boltzmann came up with a different distribution called the Boltzmann distribution, where basically said, okay, well, if you can't have things being equally distributed because you can't have anything having a negative kinetic energy, but you can go really pretty close to infinite kinetic energy, you get something that looks more like this. So it's more, and actually even that's not perfect. It's more like that, almost like it's going straight up and then it trails off like a bell curve on the other side. Well, if this line represents the average kinetic energy, how does this apply to things like equilibrium? Well, it means that if you look at the number of molecules that have a certain amount of energy, there's going to be like a ratio of molecules that have X energy versus molecules that have Y energy. So let's say that if we think about our reaction, remember we call this a potential energy surface. If this is our reactants and they have some amount of energy and then there's some barrier they have to get over, like going through the pass to get from lake level to Carson, the ratio of molecules that are at this state versus at this state is actually based on this distribution. If you give it enough time to reach equilibrium, then you actually wind up with this distribution impacting how many molecules are at the high energy state versus the low energy state. Because on average, it's easier to go from here down the hill than it is to come back up. So that means at equilibrium, we're going to have more of our molecules in this low energy state and fewer in the high energy state. The idea of applying statistics and this distribution and then applying it to something that's, a mole of molecules is basically what thermodynamics is. So it shows up everywhere because it turns out, how many of you have seen Interstellar? I love that movie, mostly because it has my favorite explanation of Murphy's Law ever, because the definition of Murphy's Law in Interstellar actually explains statistical thermodynamics. Anybody remember what it was? What? Say it again, Maddie. A lot of numbers. It's like the law of large numbers, kind of. What was it, Vinny? That's the way people remember Murphy's Law. But it's actually anything that can happen does happen. So everything happens. It's just that sometimes not very much of it happens, or it happens really, really slowly. It still happens. It just happens so slowly that if you started measuring at the creation of the universe, you still would not have a measurable amount of the reaction having happened. Right? So that application of statistics to chemistry and equilibrium is thermodynamics. Maddie? It's just storytelling. Everything from when they go into the black hole from then forward is just storytelling, just made up. There's nothing in science that says that it's wrong, but there's also no evidence to support it. So maybe black holes are the key to time travel and wormholes, but we don't know and we don't have any evidence one way or the other. There was, when that movie first came out, Neil deGrasse Tyson did he did a live tweet along while he was watching the movie, just like, stream of consciousness, anything that happened in the movie, he'd respond to it on Twitter. And it was actually really entertaining because they do most of the science in Interstellar is done really, really well. They actually hired PhDs or postdocs at Caltech to do the graphics for the black hole. And they actually helped them figure out some things. They never had anybody throw like Hollywood levels of money at trying to visualize what a black hole looked like before. And so they actually published peer-reviewed journal articles as a result of working on Interstellar, because they realized things about black holes because they actually had the money to spend on just trying to make it look right. So really cool movie. And I come back to it all the time, especially when we start talking about competing reactions. When we talk about reactions, well, this reaction happens. Well, the reverse reaction also happens. And so do 17 other side reactions that we're going to ignore because they happen, but they happen so slowly, or their equilibrium constants favor the reactants so much that we can basically ignore them, but they're still happening. And that's the more chemistry and the more science you take, the more you'll start to realize and start to really internalize this idea of the Boltzmann distribution and how everything is governed by statistics, which again, mathematicians don't like to hear because they don't think statistics is real math. All right. So we ended the last two lectures with the same ideas, right? The ideal gas law makes two assumptions. Molecules have no volume and molecules do not interact. What happens if the molecules do interact? What kind of forces do you usually have? Are they attractive or repulsive forces usually? Why do you say attractive? Magnetic fields? Bonds? Yeah, basically, if you have polar molecules, which we'll talk about in more depth on Friday, but we talked about polarity, right? And looking at Lewis dot structures and electronegativity. It's been a while, so I understand that feels like it was a long time ago. But if you have molecules that have like partial positives and partial negatives, they're going to tend to stick together a little bit, right? What happens when they stick, when your kinetic energy, your average kinetic energy drops to the point where the attractive forces are stronger than the kinetic energy moving these molecules around? What's going to happen? They're going to stick together, right? What does that look at the macroscopic level? What does it look like when a whole bunch of molecules stick together? What? If you bunch of molecules stick together, if you have a whole bunch of water molecules, Yeah, it's something like a crystal. Maybe not entirely like a crystal because maybe some of the molecules still have enough energy that they're still moving around a little bit. But what does that look like? What if we everyday life, if you see something that looks like a whole bunch of water molecules that are kind of stuck together but also kind of moving? Don't overthink it. Water. It looks like liquid, right? So what happens when molecules do interact? You get phase changes, among other things. Basically, your overall pressure is not going to be the same as what you're expecting because these molecules aren't going to be bouncing around as much as you expect. Think about if you tried to if you think of the molecules like pool balls on a pool table. If you hit the cue ball strong enough or hard enough, you wind up with them all scattering around all over the place, right? What if you tried to do the same thing except with I don't know, like I'm thinking of those little squish balls, those little squishy things, those neatos.
Stress balls.
Stress balls. If you try to do the same thing with stress balls, what happens?
Squish.
They're going to squish together, stick together, right? They're not going to fly around and bounce off the walls as much. Well, if bouncing off the walls is how we think about pressure being caused, what's going to happen if you have a whole bunch of attractive forces between the molecules? Your pressure is going to be lower than you would expect. And what about if the gas molecules do have volume? Our PV equals nRT and really our volume versus temperature graph was based on the fact that if you got to 0 Kelvin, you would get to 0 volume, right? But that's not actually true. When you get to 0 Kelvin, even if you could get to 0 Kelvin, even if getting to 0 Kelvin didn't cause a phase change, those gas molecules would still take up some space, right? So basically, the way that we adjust for this, if we really care about the sig figs on a gas, if we're talking about a system where we really need all the sig figs we can get and we don't want to make those assumptions, if we're talking about either really low temperatures or really high pressures where these molecules are bouncing into each other a lot, we have to use van der Waals equation. Van der Waals equation looks scary, but it's really just PV equals nRT. Right? So you pressure plus A times moles over volume squared. And then volume minus another constant times B equals nRT. Well, that part looks familiar at least, right? These two corrections are basically just taking into account those assumptions. Because if our gas molecules actually do take up a certain volume, then we don't actually have the full volume of the container to work with, right? Some of that volume is taken up by the gas molecules themselves. And so the way we account for that is we just subtract off a certain amount of volume. Thing is, we need to know how big the molecules are for this to work, right? We need to know how many there are and how big each molecule is. So this B term is basically how much space does 1 mole take up. So it's going to be in weird units. It's going to be in liters over moles. But it kind of makes sense when you think about it that way, because it's saying, okay, for every mole of gas, it takes up this many liters. Right? So is that going to be universal for all gases? No, it's going to be different depending on what the gas is, right? One of the first things we learned about the periodic table was we can predict like atomic radius, right? Krypton is not the same size as argon, even though they're both gases. So basically, we have to look up a value for B depending on what the gas is. And what if we have a mixture of gases? Then it starts getting really nasty, right? Because then we actually would have to look up, okay, well, if we have moles of argon times the B value for argon, and then there's also going to be minus moles of krypton minus the B value for krypton. Right? So we wind up with it getting really, really unwieldy it's not really a useful equation once you get beyond just one gas. We're going to talk about some systems today where we talk about mixtures of gases, and in general, we assume that all gases behave the same. All gases, because if they have no volume and they don't interact, then really they are all going to behave the same way, right? We're assuming that all of them have a volume of 0, then it doesn't matter what they are. What about this other term? Does this make sense in terms of our other assumption, in terms of interactions? What's going to affect the interactions of a gas with another gas? How much of it you have and how much space you have. Basically, N over V is a concentration term. It's basic, but you can also think of it as what are the odds that if you pick a spot at random, it has a molecule in it? And if you square it, it's like saying, okay, you picked a spot at random. What are the odds that it has a molecule in it? And then what are the odds another molecule also tries to be in that same spot at the same time? So it's a squared term because for molecules to have interactions, they have to bump into each other. Right? If we talk about a lot of reactions in gases that we refer to as collision theory, but you can kind of think of it like fender benders. What are the odds that you get into a single car collision or that at any given moment in South Lake Tahoe, there's a single car collision? That's going to be some constant value, right? That's dependent on how many cars are on the road. More cars, more likelihood of a single car collision, right? What are the odds of someone getting rear-ended? Now it's not just number of cars, it's number of cars squared, because you need to have 2 cars for a 2-car collision, right? And so this squared term takes into account that you need 2 things to run into each other. And this A term is basically like an energy term where it's like, okay, if 2 things run into each other, how well do they stick together? If we're talking about noble gases, they have almost no interactions, right? Because they're totally nonpolar. So noble gases, A is really, really small. But for something like water, that's a really polar molecule, it has really strong attractive forces to other water molecules. A is going to be bigger. But again, we have the same issue where we need to look up an A value for any gas that we're taking into account. If we have just one gas, it's not too bad. We can look up the A value for water and the B value for water, and we can calculate what the actual pressure is, for instance. Sorry, I almost sneezed. But as soon as we have, and so every gas is going to have its own A value and its own B value. But what about if we have a mixture of water and argon? Now there's 3 possible collisions that can happen. You can have water run into another water. You can have argon run into another argon, or you can have water run into an argon. They're all going to have a different A value. And really quickly, this turns into a monster of an equation. It already is a pretty intimidating equation, right? But basically, it gets to the point where you can't solve anything as soon as you have a mixture of gases. So if we have just one gas, it's okay to solve as long as I don't ask you to solve for moles or volume. If I ask you to solve for moles or volume, this gets to be really a nasty equation, right? You get a quadratic, you have to FOIL stuff, use a solver or something like that. Solving for pressure or solving for temperature isn't too bad. So let's do an example where we look at this with water vapor. If we have 1 mole of water in 22.414 liters at 0 Celsius, what should the pressure be if we just use PV equals nRT? If we just use PV equals nRT, remember this volume was a significant volume. at standard temperature and pressure, right? So if we use our standard PV equals nRT, we should solve for pressure equals exactly 1 atmosphere within sig figs. If we take these adjustments into consideration, we have to go look over here. We have to find water. We have to find A for water. Then we have to find B for water. We have to plug them in. We're going to get something like, so P plus, what does it say, 5.46, thank you. Times 1.0000 moles over 22.414 liters squared times 22.414 liters minus moles, so minus 1.0000 times 0.305. That's going to be in liters over moles. So then our moles is going to cancel that out. I left off our units on A. It's liters squared times atmospheres over moles squared. All of that time equals 1.0000 moles, 0.08206 liters ATM over moles Kelvin. And at least our temperature is easy to convert, right? 273.15 Kelvin. We're just trying to solve for pressure. No big deal, right? Just a whole heap of arithmetic and algebra. So you can see why we don't use this first. This is a really, really specialized equation. It's an important equation because it shows us and it reminds us how we can correct for those two assumptions if we can't use them. But it's not really something we're going to use on a regular basis, especially not if you're trying to solve for n. If you're trying to solve for n, you're going to just want to get a solver. This is not something I would ask you to solve on the time part of the test. And again, it basically doesn't work unless you blow it up to fill the entire board as soon as you have a mixture of gases. If you're interested, we can actually work out what the correction terms would be for a mixture of two gases, but it's not going to be something we want to solve for. And it's not something that you would even be able, like, they don't make tables of van der Waals constants for combined gases. You would actually need to have a different A value for each of those three terms. If we had that mixture of argon and water, each one of them is going to have a different A value. And I've never seen, I'm sure that there's a table somewhere in the textbook that has mixed van der Waals constants, or van der Waals constants for mixed gases. But that's not the sort of thing that I really want to be a part of. I guess that's not true. We could calculate that. We're doing computational chemistry with my organic class right now. And that is the sort of thing that we could calculate. We could calculate a value for A. But it involves some quantum mechanics, and we can't calculate it by hand. You need a supercomputer for it. So we're just going to ignore that. Just as soon as I said it's not something I want to be a part of, I realized that's exactly what I did for 5 years in grad school. I'm not even going to crunch the numbers on that one because I don't think it's worth it. If you did run the numbers, did anybody get a final answer? It winds up being really close to 1 atmosphere. basically, unless you care about like 5 sig figs plus and you're at really high pressures, you don't need to use this. It's worth noting though, so as soon as you start getting into really large values of N, or where N over V is a really large number, then it starts being significant. And basically, again, I'm not going to ask you to solve it, but it's worth noting because that's where the ideal gas law falls apart. As soon as N over V starts getting really big, then you can't use just regular PV equals nRT, because you're not going to get answers that are right, even if you ignore phase changes. And so that would be a good thing to write down. The ideal gas law falls apart when these two assumptions aren't true anymore. And mathematically, you can look at it like when N over V starts getting really large, when your ratio of gas molecules to volume, it starts getting large. In other words, when everything starts getting cramped, you're going to have more collisions, which is going to make this first term bigger. And your moles of gas are going to start taking a larger and larger portion of your total volume. Okay, so high pressures, high concentrations of gases, large number of gases in a small volume when ideal gas law falls apart. And as I mentioned, don't try to solve for N or V by hand. It's not worth it. Let's talk about what happens when we have mixtures of gases. The broken character there is supposed to be a reaction arrow, as you could probably figure out. So we put carbon monoxide with hydrogen gas, we get methanol. We can do stoichiometry with this. And if they're all gases, it might be useful to think about it in terms of pressures. So if we're using the ideal gas law, are there any A or B terms in there? Nothing in there. Depends on what the gas is, right? So in other words, it doesn't matter if you have a pure gas or a mixture of gases. PV equals nRT works the same way. If we're making the assumption that the gases don't interact, then they're all interchangeable, which means we can treat a mixture of gases like it's just separate pieces of gases. We can actually look at our total pressure as just being the sum of our partial pressures. So in this case, before the reaction starts, we've got carbon monoxide and we've got hydrogen. Our total pressure in that system is the sum of the partial pressures. Right? So it's really just like having a concentration for two different things at the same time. Mathematically, it works the same way. But if you see the term partial pressure, or if you see it written like this, that just means we're talking about pressure of this particular compound, right? So we saw that a little bit when we started looking at equilibrium constants, Kp, right? If we wanted to write the equilibrium expression for this reaction, what would it look like? So if we've got, let's balance it first. CO plus H2 goes to CH4O. Just needed 2 there, right? What is the equilibrium expression going to look like in terms of concentration? Kc, what's the first rule of equilibrium? Products over reactants, good. So concentration of methanol over concentration of hydrogen squared concentration of carbon monoxide. Kp for the same reaction is the exact same expression, except instead of concentrations, you write it as pressures. It's the same reaction or the same expression, except in pressure units. So Kp for the same reaction would be pressure of methanol over pressure of hydrogen squared times pressure of carbon monoxide. Looks the same though, right? Basically, pressures and concentrations can be treated the same way in a lot of cases because they're proportional to each other. As long as we're making those assumptions in the ideal gas law, which we pretty much always are. So for this reaction, this is not, what type of reaction is this? Do we know this type of reaction? I asked that, but then I realized it's not a combustion reaction. 9 times out of 10, when I put carbons on the board, it's a combustion reaction, right? This is not a combustion reaction. Turns out it is a redox reaction, but it's beside the point. We can look at oxidation states. If we treat everything in terms of masses, we know how to do stoichiometry with that, right? What about if we want to know the final pressure in the system? What's going to wind up happening? If we want to know the total pressure at the end, what do we need to know? We have a few things changing here. What's being held constant and what's changing? Temperature and volume are held constant. So we cross them off. So if we want to know the final, if we know the starting pressure, we can figure out our starting number of moles too, right? Just for molecular weights. If we want to know the final pressure, we need to know the final number of moles. So how can we solve that? 5.001 grams, 34.502 grams. It's a stoichiometry problem, right? What's the first thing we do with stoichiometry problems? Find moles. And then since we're going to have 3 different things changing at the same time, this is a good candidate for an ice table, even though it's not an equilibrium problem. Because we're going to need to know the total moles at the end, right? Let's see, how do we get to moles though first out of our reactants? Let's not get ahead of ourselves. Molar mass. So molar mass of carbon monoxide is 12 plus 16. So we've got a little bit more than a mole here. We've got about 2.5 moles here. Did somebody punch it into the calculator yet? 5.001 grams. Every 2.015 grams is 1 mole H2. Then do the same thing here, 34.502. We get 28.010 grams is 1 mole. What do we get?
For comes to us. 1 point.
And this is really close to what's going to run out first. if you double this, you're gonna get 2,462. So you're gonna run out of this one first, just barely. Right? If we're just doing a limiting reactant problem here. 2.480, 1.232. So that's enough to fill out one side of our gas law equation over here, right? That's enough to get N1. And we have P1 given, right? How do we get N2? Figure out what gets used up, figure out what's left over. We need our total moles at the end. And since we care about everything's final number of moles at the end, an ice table works well. Because we can say, if carbon monoxide is running out first, that's going to be enough for us to solve for X right there. We're all pros with ice tables now, right? No? If it's getting used up, it's a positive or a negative? Negative. If it's getting produced, it's a positive. We use X for everything. We just plug in our coefficients, right? So that if we want to know our final moles of hydrogen, we just solve for X and we just do 2.480 minus 2X. Right, so what's different about using an ice table for stoichiometry versus equilibrium? At equilibrium, do we ever get to zero of anything? Equilibrium, we're always going to have some amount of something left over. In this case, though, we're saying we're going to treat it like it's a stoichiometry problem. For a stoichiometry problem, whatever your limiting reactant is going to end at zero. So as soon as you figure out what runs out first, you can fill out that column and solve for X. So X is 1.232. So we said 2.464. So that's going to be 0.016 moles left. And over here, 1.232. So N1 to be the sum of everything, right? Everything we started with. So just add these together. So N2 is just adding these up. So 2.248. P1 was given 1.51 ATM.
Is that 1.2?
Yes. Thank you. So we can solve for P2. Without punching any numbers in your calculator, can anybody come up with a ballpark for what P2 is going to be? We have about a third of the moles that we started with, right? So that means our pressure should be about a third of what we started with. So somewhere around 0.5. Within sig figs. All right, so questions on how we got to any of these numbers? You can always use an ice table for a stoichiometry problem. But remember, most of our stoichiometry problems, we mostly cared about one product. or how much excess was left over. If we only really care about one of these concentrations at the end, it doesn't always make sense to write an ice table, because why bother if we don't care about those numbers? But anytime we have a bunch of things changing at once and we care about all of them for whatever reason, an ice table is a really useful tool. It's always useful in equilibrium, because equilibrium always depends on everything at the end. Stoichiometry, sometimes we don't care about an ice table though. All right, anybody get a final answer for P2?
I know.
All right. Let's talk about vapor pressure a little bit. So basically, finishing up talking about gases is going to be a couple of specific gas law applications and how they apply to things. So it's a little bit disjointed. We talked about van der Waals forces. We talked about partial pressures. Now we're going to talk about vapor pressure. Vapor pressure is basically, not basically, it's an equilibrium process. Turns out phase changes are equilibrium processes, especially if you're holding at a constant temperature. So normally we could write the reaction of water evaporating like this, right? What would the equilibrium constant be for this? What's the first rule of equilibrium? Products over reactants. What's the third rule of equilibrium? Solids and liquids don't count. So if we wrote Kp for this reaction, it would just be pressure of water as a gas over 1, because liquids don't count. And I know somebody asked me a question on the quiz, why is it that solids and liquids don't count? Does anybody remember our reasoning? Why don't solids and liquids count? Does the liquid water have a vapor pressure, or does it have a pressure of its own? It doesn't have a pressure until it turns to a gas, right? But even in terms of concentrations, solids and liquids have constant concentrations, right? The density of gold is the density of gold. So it doesn't really matter. They're not going to change based on equilibrium. So they fall out of this because we only put things that can change into our equilibrium expression. So what this says is that at a certain temperature, the equilibrium constant for this reaction is just a pressure. They call this pressure vapor pressure. So if you have a closed system of water, think about just a water bottle in your car. Is there humidity inside that water bottle? Yeah. And is it going to be a constant? Why not? Because if your temperature changes, that's going to change this value, right? Remember, temperature factors in over here. So different temperatures are going to have different vapor pressures. But if you keep it at a constant temperature, then we can basically say that at this temperature, the vapor pressure of water is X, is this number of atmosphere or torr. What that refers to, or we see that showing up in meteorology. How do we measure humidity in meteorology? Anybody know? Not measured directly, but how is it reported? Like if it's going to be a really high humidity day for us, we'd say it's going to be 80 degrees at 40% humidity, right? That percent is what percent of the equilibrium vapor pressure is for that temperature. So 40% humidity at 80 degrees is not the same as 40% humidity at 60 degrees. But it's a good way of measuring humidity in terms of how it feels to us, because why is average humidity level important to humans? Real temperature versus feels like, why does it feel hotter when it's humid? There's more moisture in the air. But what does that slow down? The evaporation of your sweat. Basically, your sweating doesn't cool you down if it's a really humid day, because it just sits on your skin because you're already close to the vapor pressure for water. Right? So, you know, in Minnesota, where my wife's family is from, they regularly have 90-90 days, they call them, where it gets 90 degrees with 90% humidity. And it's just miserable. You get out of the shower and you dry off and it feels like you didn't even touch a towel yet. You're just soaked the entire day. It's really miserable. There's really nothing to do on a day like that other than submerge yourself in the lake and drink cold beverages for as long as you can. And then hopefully it cools off at night. Y'all are a little spoiled because it gets nice and cool here at night. Still, even when we have a hot day, it still gets cold at night. Yeah, we have 20-20 days. In Minnesota, it'll be high of 90 degrees with 90% humidity, and the low will be 78 degrees with 90% humidity. All right, the other reason that vapor pressure is really important is because it does change with temperature. We can look up these values. Basically, if we look at, these are the saturated, these are 100% humidity at different temperatures. If you get up to 20 Celsius, so room temperature, this 100% humidity is about 17.5 torr. Not that high. But look what starts going as you start getting higher and higher temperature in Celsius, you start getting higher and higher equilibrium pressure. What do you suppose happens when you reach 760 pressure? What happens what is 760 torr? 1 ATM. When your vapor pressure equals your atmospheric pressure, something happens. Basically, you get to the point where your average molecules have enough energy, they're no longer being forced to stay as a liquid. What does that look like? Phase change. Basically, when your atmospheric temperature, when your vapor pressure equals your atmospheric pressure, is your boiling point. So that's why water boils at a different temperature up here. We have less atmospheric pressure. We only need to get to about 0.8 atmospheres before water starts boiling, compared to sea level where they have to get to 1 atmosphere for it to start boiling. This is also exactly how a pressure cooker works. Because if you boil food, you're limited to cooking at the temperature that water is boiling at, right? Because as long as the water is boiling, your temperature can't get any higher than that, right? If you increase the pressure in that system, water will boil at a higher temperature, which causes everything to happen faster. So something like, I don't know, braising short ribs can take a really long time, could take 5-6 hours if you're doing it in a smoker where you're limited at the boiling point of water. It takes even longer at altitude. But if you put it in a pressure cooker, you can do the same thing in half an hour. because you're changing that atmospheric pressure, which allows your temperature to go up. All right. Questions about vapor pressure. I know it's kind of a weird concept, but it really is just gases and equilibrium where they meet, kind of. I don't think this is a question that I'll ask in this class. But this does mean that we can actually solve for this delta G term if we have the vapor pressure at two different temperatures. Because if we have the vapor pressure at two different temperatures, we can actually turn this into a linear form. So we can say vapor pressure, if we say vapor pressure equals E, and we're going to change it from delta G to delta H of vaporization, because that's the term that we've used for energy here, over RT. We rearrange that. This was the example that I used the other day of how we can take a weird looking function and turn it linear, right? We take the natural log of both sides and rearrange it a little bit. We get natural log of vapor pressure is equal to minus enthalpy of vaporization over R times 1 over temperature plus a constant. Well, this is really just a linear equation at this point. We can do point slope form. We can take any two data points and use it to find the slope of the equation, right? So if you plug in vapor pressure at temperature 1 and temperature 1, we can actually rearrange this a little bit and we can actually get something we can solve for. The other version of this looks like P1 minus P2 equals the slope times 1 over T1 minus 1 over T2. Well, as long as I give you the pressures and the temperatures, you can solve for the slope then, right? So we actually do this lab in Gen Chem where we actually measure the vapor pressure at different temperatures. And if you know the vapor pressure at different temperatures, you can plug this in and you can either plug it into the 2-point version or you can actually plot it in Excel and get the slope of the line through a linear regression. But we can actually measure the enthalpy of vaporization by looking at the vapor pressure at two different temperatures. So that enthalpy of vaporization is not just some measured number, or not just some number in a book somewhere. We can measure it directly. We just have to do a little bit of algebra and measuring to do that. All right. Last topic on gases. It's going to come back to thermodynamics and probability again. If we're talking about a discrete object in physics, we can calculate the kinetic energy of that object by using the kinetic energy equation, which is just 1/2 mass times velocity squared. Now, in physics, you see this all the time and you get something like a bowling ball or a tennis ball. It's pretty easy if you have a measurable mass in one object to figure out the kinetic energy for it, right? Except we don't have one object if we're talking about gases, do we? We have, they call a canonical ensemble is the thermodynamics term for it. But basically, we get a Boltzmann distribution of particles where this equation still holds true, but it's the average velocity that we solve for. And it's really at the same temperature, it's the kinetic energy. We're measuring the average kinetic energy, not the average speed. But if we have this equation, if we know the average kinetic energy, trying to be consistent here because there's a couple different notations you can use. The average kinetic energy of a molecule is going to be equal to the mass of that molecule times the velocity of that molecule squared. So at the same temperature, how can we figure out what gas is going to be moving faster? Temperature is proportional to kinetic energy. So when I say at the same temperature, we're really saying at the same average kinetic energy. So what's going to be moving faster? Argon or helium? You don't sound convinced.
Argon.
Well, it's one of the two. Think about it in terms of discrete objects. If I gave a golf ball the same amount of energy as a bowling ball, which one's going to be moving faster? The golf ball. Right? So higher mass means slower velocity for the same amount of energy. So helium molecules are going to be moving faster than argon.
So it's like measuring force.
It's a little bit like measuring force. So think about this. Has anybody ever had a helium balloon that you got filled up at the same time as a balloon you blew up yourself? Sure. Which one stays inflated longer? Why? It goes up onto the ceiling and then you can't get it. It stays up there. But the helium balloons don't stay up there forever, right? Especially if it's not like the Mylar ones, if it's just a regular birthday party balloon. The helium balloon will deflate faster because they're moving faster. So they call that process effusion. Gases effuse according to their velocity. The faster they move through stuff. Because what's really happening with the helium balloon is the helium particles, the helium atoms, are kind of working their way through little pores in that plastic. So why different, like really cheap balloons won't hold helium as well as good balloons, expensive balloons. Because the expensive balloons have smaller pores that slow down the helium. But basically, the larger a molecule is, the slower it moves through those pores. Partly because it's bigger and partly because it's moving slower. Right? And so we don't really solve for these values. So if I go back and look at these equations, in order to solve for the actual velocity, we actually have to do things in terms of atomic mass units instead of grams per mole. And we have to wind up not necessarily being a useful value to solve this. But we can compare them to each other. And the rate of one molecule moving through a system versus the second molecule is going to be equal to 1 over their masses squared. Or sorry, square root of their masses. And so if we looked at nitrogen versus helium, how much faster does the helium move through the balloon than the nitrogen? We look at their masses. So we want to say, we're not actually going to put a number to the rate. We're just going to look at it as a ratio. We can calculate that, but it involves more math, and this isn't a statistical mechanics class. Mass. So the molecular mass of nitrogen goes on top, the molecular mass of helium on bottom. It's that 1 over square root relationship. What's the mass of nitrogen? So N2 is going to be about 28, right? and helium's around 4. So those are actually convenient numbers if we're just doing estimates in our head. Because we get, that's a ratio of about 7, right? So the rate of helium compared to the rate of nitrogen about the square root of 7, so about 2.5 times faster. So everything else being equal, helium will move through a membrane, will move through a room about 2.5 times faster. And this also applies, the same math applies to diffusion. So effusion is moving through a barrier, through a hole. Diffusion just means like normally moving through an open space. But if we had a way to measure how, if we opened up a helium tank over here, eventually there's going to be helium molecules spread evenly through the whole room, right? That process is called diffusion, not effusion, but it's the same math. Helium will move through the whole room about 2.5 times faster than nitrogen would move through the whole room. And the larger your molecule is, the slower it diffuses. Just because it's straight up moving slower. It's got a smaller velocity, so it takes longer to get from point A to point B. All right. We have another practice problem. This one's kind of fun because it involves geometry and spheres, but it's 4 minutes left to go and it's nice outside. So I don't feel like doing this one right now. We'll do this one at the beginning of class on Friday.